Dimension of a vector space. Let V be a finite dimensional vector space over the field K, where K is the field of real numbers, or K is the field of complex numbers. Firstly, a definition. The definition of the basis of a vector space, a system of vectors that denoted by B, vectors V1, V2, Vn is a basis of V if V is the span of B, and the second condition, B is a linearly independent system of vectors, B linearly independent system of vectors. Explicitly, in more details, firstly, for any vector x from V, there exists x1, x2 up to xn in K, such that x can be written as a linear combination is x1 v1 plus x2 v2 plus so on up to xn vn. And B is a linearly independent system of vectors, so a linear combination of these vectors, alpha 1 v1 plus alpha 2 v2 plus so on plus alpha n vn, can be zero only in the case when all the coefficients are zero. From this, it follows that the coefficients, all the coefficients, alpha 1 equals alpha 2 equals so on equals alpha n, are zero. A remark: representation of an arbitrary vector x as a linear combination of the vectors of the basis is unique. The coefficients are uniquely determined in this formula. In star, the coefficients xk are uniquely determined. Indeed, if we assume that a vector x admits two such representations, x equals x1 v1 plus so on plus to xn vn, and the same vector, another representation, x1 prime v1 plus xn prime vn. From this relations, we get that this linear combination x1 v1 plus xn vn equals x1 prime v1 plus xn prime vn. This equality can also be written as x1 minus x1 prime times v1 plus so on plus xn minus xn prime vn equals 0. So we have obtained the linear combination of our vectors equals to 0, but we know that this is possible only in the case when all the coefficients are 0. So we must have x1 minus x1 prime must be 0, so on up to xn minus xn prime equals 0, but from this we get x1 equals x1 prime, xn equals xn prime. So the representation of a vector as a linear combination of the vectors of a basis is unique. The coefficients are uniquely determined. They are called the coordinates of x in the considered basis. Now, in order to prove that for a vector space, any two bases have the same number of vectors, firstly, we prove the following result. Theorem. For the considered vector space, let M theorem. Let M containing the vectors v1, v2 up to vn be a system of linearly independent vectors. And we consider as a spanning set for V containing the vectors w1, w2 up to wk spans V. From this, it follows that firstly, n is less than k. Number of vectors here is lesser than the number of vectors from S. And second, the set of vectors M can be extended up to a basis of V by adding vectors taken from S. Let us prove this proof. Firstly, M is a linearly independent system of vectors. We know that it cannot contain the null vector. Null vector cannot belong to M. Now, the first step, step 1. We have that S containing the vectors W1, W2, so on WK spans V. if we add here an additional vector v1 w1 wk, this evidently also spans v. Now, since v equals span of S, it follows that the vector v1, this vector, is v1 is a linear combination of the vectors w1 up to wk is alpha 1, w1 plus so on, plus alpha k wk. But since v1 is different from 0, from this it follows that at least 1 of alpha alpha I is different from 0. Let us consider that alpha I1 is different from 0. Then from this relation, from this we get that Wi1 is a linear combination of the other vectors. From this equality, we can express Wi1, a linear combination of the other vectors from this system, from V1, W1 up to WK. So if we eliminate such a vector from this spanning system, we get also a spanning system. So we get, let us denote by S1, the system of vectors containing V1, W1 up to WK, and we have eliminated Wi1. And we obtain that this spans V. Now, we inserted the first vector here. Now step 2. Step 2. From this it follows that the system of vectors V1, and we insert V2, and here is W1 up to WK, and minus, we have eliminated Wi1. This also spans V, but from V equals span of S1, it follows that the vector W2 will be a linear combination of these vectors. We get V2, which is different from 0, is a linear combination of the vectors. Let be beta V1 plus, let us denote the other coefficient, gamma j, wj. V2 expressed as a linear combination of the vectors of this spanning system. Uh, Firstly, from this we can remark that at least one of gamma j is different from zero. If all the gamma j are zero, then V2 is a linear combination of V1. But this is not possible. None vector of this system is a linear combination of the other vectors. Let gamma I2 be different from zero. So from this relation, we can express the Wi2 as a linear combination of the other vectors from this system. So if we eliminate such a vector from this system, we get also a spanning set for V. We get that, let us denote by S2, the system of vectors obtained from this one by eliminating this. That is V1, V2, W1 up to WK, and we have eliminated WI1, WI2. Now we continue with the step 3. We continue in the same way. Step 3. And S2, the system continue to spans V. From this we have eliminated a vector which can be expressed in terms of the remaining vectors. So this is continues to be a spanning system for V. Now from this we get that the following system of vectors, V1, V2, V3, the next vector. And we add to this system of V3. And here is W1 up to WK. And we have eliminated WI1 and WI2. This span V. This system spans V, and we have added this vector. But V is the span of S2, and from this we get that V3 will be a linear combination of these vectors. Let be a V1 plus B V2 plus a sum CI WI. Now, in a similar way, we can see that at least one of CI is different from zero. In the opposite case, V3 is a linear combination of V1 and V2, but this is not possible. Here we have a linearly independent system of vectors. Let Ci3 be different from 0, and from this relation we can express Wi3 as a linear combination of the other vector. We eliminate Wi3 and after the elimination of this vector, the obtaining system, which is S, step 3 is here, S3, 3, which contains V1, V2, V3, and W1, Wk. We have eliminated 3 vectors, Wi1, Wi2, Wi3. This spans V, and we can continue in this way, and to insert, evidently we can insert all of these vectors in this way. After n steps, if the intersection of these two sets is the empty set, after at most n steps, we get Sm, Sn, a system of vectors of the form V1, V2, up to Vn, and W1, Wk. We have eliminated Wi1 up to Win. This spans V. It contains all these vectors, and so it is necessary K to be greater than or equal to n. And from Sn, which spans V, from Sn we can extract a basis by eliminating each vector which is a linear combination of the vectors written before. In this way, these vectors remain in our set, but we have to eliminate some of the vectors W after these eliminations, there continue to remain such vectors. We have already presented in another video clip how to extract a basis from a spanning system. We analyze the vectors. If the second vector is a linear combination, we eliminate it. If not, it remains. Then the third way. But in our case, none of these vectors is a linear combination of the previous, and we have to continue to analyze here. If a vector here is a linear combination of the previous, we eliminate it, and in this way we arrive at a basis. So M can be extended up to a basis of V by adding, if necessary, some vectors from S. Now we use this theorem in order to prove a very important result, namely any two bases of a vector space contain the same number of vectors. Any two bases of a vector space contain the same number of vectors. Proof. Let us consider the two bases of our vector space V, V1 up to Vn, basis in V, a second basis, V prime, V1 prime up to Vm prime, also basis in V. Both of them are systems, linearly independent systems of vectors, and also spanning systems for V. So by using the previous theorem, we get that n is less than m, and also m is less than n, and from this we get n equals m. Now a definition. Dimension of a vector space V over the field of scalars K is dimension of V. We can also indicate here, if necessary, the field of scalars of V, or we can write if the field is known, just, and this is equals number of vectors of a basis. This if V is not the null space. We know that the null space does not admit a basis, and the dimension is 0 if V is different, and is 0 if V is the null space, the dimension. Now a result concerning the dimension of a subspace of a vector space theorem. if W contained in V is a subspace, vector subspace, then the dimension of W is less than or equal dimension of V. Proof. Let BW equals W1, W2, up to WM basis in W, and V, V1, V2, up to Vn basis in V. This system of vectors, BW, is a linearly independent system in V. From a linear combination can be zero only in the case when all the coefficients are zero. And V spans V, and from our previous theorem, we get that M is less than N. And this can be extended up to a basis of V. Particularly from this remark that this can be extended up to a basis of V, we can see that in the case when remark W is a subspace, but the dimension of W equals dimension of V. From this we get that W, this subspace, coincides to V. We know that the basis of W can be extended to a basis of V, but in this case we know that it already contains exactly the number, the dimension of V, so it is at the same time a basis of V. So the two spaces, this is a basis in both of them, so the two spaces coincide. Now, just an overview on the presented results. We end by an overview. We have here is an overview, the definition of a vector space, vector subspace, spanning set, definition for a linearly independent system of vectors. Here is a possibility. These are sufficient conditions in order to have a linearly independent system. If a system does not contain the null vector, and Vk is not a linear combination of the vectors written before it, and this happens for any k, then we have a linearly independent system. These are necessary and sufficient conditions to have a linearly independent system of vectors. Here another result we have used in this video clip. If this system of vectors spans V and one of the vectors is a linear combination of the other vectors, then after eliminating it, we get also a spanning system for V. Here is the content of our video clip, the definition of a basis, and our first theorem, and then the fact that any two bases of a vector space have the same number of vectors, the definition of the dimension of a vector space, the dimension of a subspace is less than or equal to the dimension of the whole space. Okay, and this overview in preparation, we can find it on my website. Here is my website where you can find this and my previous video clips. And also an introduction to complex analysis, differential equations, Fourier analysis, some notes on the mathematical description of quantum systems. Thank you very much.